Thank you very much for the introduction. So I'm going to talk about partially fault-tolerant quantum computing architecture for early FTQC era. This is a collaboration that my research colleagues in Japan, Fujistu Research at Japan, did with Osaka University. And it's based on this research paper, which is available in arXiv. It first came in March 2023. So before I dive deep into the result itself, I just wanted to reiterate Fujistu's quantum computing effort. This was covered in great detail yesterday in the keynote speech of Dr. Shintaro Sato. But in case you missed it, this is just one or two slide snippet of what we are doing. So we work on every layer of quantum computing stack, right from devices to platforms, software, and applications. When it comes to hardware devices, we're working on two. We are actually investing significant resources on two hardware modalities. One is based on superconducting qubits in collaboration with RIKEN in Japan, and the other is diamond spin-based device in collaboration with TU Delft. And we also work on software and application. We have extensive research collaboration with leading research institutes and industry as well. So with QNASys, we do algorithmic applications. With Keysight Technologies, we actually work on quantum error mitigation techniques for NIST devices. And the one that I'm currently talking about, the work is a part of the collaboration that we did with Osaka University in quantum error correction. Okay. I also wanted to sort of talk a little bit about superconducting-based quantum device. We have actually successfully developed a 64-qubit superconducting device. The chip is available in our booth along with our diamond spin mockup. So if you want to actually have a look and talk to our researchers over there and discuss about it, you're more than welcome to do it. This press release was done 2 months ago, and this is a joint work with RIKEN. And in future, we plan to extend the 64-qubit device to over 1,000-qubit device using, high-density packaging and also improve one-gate fidelity. And then we have a sort of a hybrid platform where we have a 40-qubit quantum simulator along with our superconducting-based device, which together we'll use and to conduct joint research activities with institutions and industry. Okay. So let me now start talking about this sort of paper. So I don't have to impress upon this audience that quantum error correction is the biggest and grandest of challenges, software or algorithmic challenge that we face in realizing practical application of quantum computing. You have, of course, there are several challenges that you face in developing hardware, scaling it, improving upon gate fidelity, for instance, but noise will occur. There are various sources of noise. Their sources of noise could be fluctuation in control signals, interaction with environment, and you need to basically sort of mitigate or correct these noise. So as a very crude illustration, suppose I can actually implement a gate operation with 99.9% fidelity, in the sense that once you apply the gate, instead of getting the correct output, you get the correct output, you get the output which is 99.9% close to that correct output. Now, suppose you have 20 qubits and you want to actually run 50 qubit operations, 50 gate operations. Then after you do this, the error basically keeps on compounding, and at the end of the day, your sort of ideal output and the output that you get, output state, quantum state you get, they have very less overlap, 1/3. Okay. So this is very challenging, and in the NISQ era, people have been using various error mitigation and suppression techniques to sort of improve upon this performance. However, if you want to actually implement, you realize practical applications of quantum computing, you do have to sort of think about quantum error correction. And it's similar to what happens in the classical case. You basically have a physical qubit that stores some information, and you basically encode into a block of physical qubits that you call a logical qubit. And then if anything happens, I don't know whether, okay. So if any error happens on one of these physical qubits in this block, you try to detect it and by syndrome measurements, and then sort of use some post-processing technique to correct it. Okay, so this is the process that basically sort of everyone follows. And for 25 years, we have actually sort of built several quantum error correcting code, starting with short 9-qubit code to this well-known surface code, which appears to be highly implementable on actual hardware. We also have recent developments in quantum LDPC codes, which are very promising for fault-tolerant quantum computing devices. Okay, so quantum error correction is essential for practical applications. However, at the moment, quantum error correction also needs enormous amount of resources in terms of physical qubits as well as gate operations. So you cannot hope to implement any quantum error correction scheme on a NIST device, which basically probably will have maybe 1,000, 2,000 qubits. And when you are actually in this regime of fully fault-tolerant quantum computing, you can possibly implement over, let's say, 1 million, 10 million, or 1 billion physical qubits. You'll be able to sort of realize quantum error correction, existing quantum error correcting schemes, and you will be able to generate applications, okay, once those things are realizable. However, there is a regime which we innovatively call as Early-FTQC era, which probably has 10,000 or 50,000 physical qubits, where if you do not implement any QEC protocol, it is not going to be any useful. And the thing is that basically in that particular, when you have these 10,000, 50,000 physical qubits, you can sort of construct, you can actually implement some QEC technique to generate probably, 100 or 200 logical qubits, which might be useful for some practice. So we need to actually find out a way to ensure that in this particular era, you are able to sort of construct logical qubits. And that's what we're doing. We're actually coming up with an architecture that is tailor-made for this Early-FTQC era. Okay, so let me briefly talk about the conventional fault-tolerant quantum computing architecture. We have a universal quantum gate set, which is these 4 gates, 2-qubit control NOT operation. Then you have a Hadamard gate and a phase gate, and then a special gate T gate. So if you basically just use the first 3 gates, the circuit formed by those first 3 gates, and then measuring them in computational basis, it can be efficiently simulated classically. Okay, so the power of quantum computing comes from realizing T gate, or sort of using T gate in the computation. And of course, all of these universal gate set, these are physical gate set, they have a logical counterpart. So if you basically have an error correcting scheme, you'll have a logical C0 gate, you'll have a logical phase gate, Hadamard gate, as well as logical T gate. And they can be reliably implemented in this conventional FTQC architecture. There are several such schemes and corresponding logical gates. However, one of the problems is that this particular T gate, when you implement it logically, it requires huge amount of physical qubits and gate operations to implement. Okay, so the way it is done is it's a 2-step process. The order is a bit reverse. First of all, you actually create this so-called magic state via a distillation circuit, and the idea is that you have a bunch of these noisy logical magic states, magic states encoded in logical qubit, and noisy means they're not exactly the magic state, but not in sense of error correction. And then you run some sort of distillation circuit on it to get one clean magic state. And this is a very special state to implement T gate. And then the idea is that you basically use a gate teleportation technique, which is run this circuit in the block, where you actually use the magic state as a control and apply a control NOT operation or the target state, and then you measure it, and depending on some measurement, you apply some operation, and magically the T gate will be implemented. Okay, so the output of this measurement followed by, I don't know what. Okay. Okay. Anyway, so the output of the second logical qubit will be, a T gate, a logical T gate applied to the input state. To realize this, you need to have a sort of you need to use several logical qubits simply because you have to create this magic state. So there are processes which basically use 15 or 30 noisy magic state to create one clean magic state. And then, of course, since you're using logical qubits, you're using a huge amount of physical qubits. So, and of course, as well as, the circuit depth is also huge in this particular case. And that's just to implement one T-gate operation. And that's why when there are many papers where they talk about, when they sort of talk about NISQ applications, they try to reduce the number of T-gate operations. So they want to analyze how many T-gates they are using, because each T-gate invocation is very costly. Now, quantum computing, if you want to basically implement it, you have to actually implement an arbitrary phase rotation, which means that you're actually rotating a state by an angle theta in the complex plane. And the way it is done is sort of by using Hadamard gate and T-gate in conjunction. So you start using Hadamard and T-gate, it rotates by a certain angle, and you keep on doing it. And after a certain while, it will basically converge to the ideal angle theta that you want to rotate. Now, T-gate, of course, takes a lot of logical operations, a lot of physical resources to implement logically. So if you want to implement this phase rotation logically, you will basically again have enormous amount of physical qubits is needed to do it. So in essence, many cases it requires 100 times, or some cases it requires 10 times, but 50 times on average invocation of H and T gate is required to implement an arbitrary rotation. Okay. So this thing, if you try to do it in an early FTQC era, this is very costly. So what we actually come up with, we came up with a new architecture where we just get rid of this logical T gate and instead sort of have a phase rotation gate. Okay. So we directly implement the phase rotation gate on in this newly developed architecture, and the benefit of this is that the number of physical qubit we require is 1/10 of what is required if you want to implement phase rotation using T gate and H gate. And of course, the number of gate operation is also reduced by 1/20. Okay, but this is, of course, it comes at a cost. Okay, so if you look at this picture, in the conventional FTQC architecture, every gate is logically implemented, but in this newly developed architecture, phase rotation gate is not logically implemented, in the sense that the error over there will be a little bit larger than what you get when you implement the logical T gate. Okay, but the method is very similar to what we did when we were implementing T-gate. But in this particular case, we use again the gate teleportation technique, but we have an ancilla state, which is sort of where we sort of try to minimize some error. So it is again in this logical state 0L plus e to the power I theta 1L. And then you run this circuit, and by the end of the circuit, with probability half, you get the correct state. So arbitrary phase rotation, with probability half, and with probability minus half, you rotate by an angle of minus theta instead of plus theta. However, in this particular case, you do not use any distillation, so you reduce. That's why you reduce the number of physical qubit that is required. The issue is that the ancilla errors are going to be more than what you would imagine if it was a T-gate operation. Okay, so I'm just gonna sort of tell briefly about how this phase rotation gate is implemented. You have sort of a target angle theta, and the first thing you do is you basically prepare this logical ancilla state. So the first step is basically you use 4 qubit and use a 4 qubit surface code to encode into, by running this circuit to encode into a theta, and then you map this theta to the larger surface code, so where, in which you actually construct a logical qubit. So the final, the right-hand side figure is basically theta implemented in a logical qubit. Of course, the error, what this achieves is it achieves high accuracy in the sense that you use you actually reduce the physical error rate by 1/8. And it is sort of a trade-off between the number of physical qubit and gate operations you require versus the error that you want to achieve. So if you want to sort of reduce the error further, you'll basically sort of be using a different technique to do it. And then the process is very simple. You repeat until you succeed in implementing the arbitrary phase rotation. So you have prepared this ancilla state in a logical qubit, and then you run this circuit on the right. You try it with probability half. You'll be correctly you have done, so you have correctly implemented the angular rotation, the theta. With probability half, you rotate it by an angle minus theta. So what you do is you sort of retry again. And in this case, since you know that you have reduced, you have rotated by an angle minus theta, you overcorrected by sort of preparing an ancilla state with 2 theta. Okay. So next time your rotation will be by 2 theta. If it fails again, 4 theta, then 8 theta, and that's how you do until you sort of get the correct rotation. And it so happens that if you actually calculate the average in 2 trials, on average, you will succeed in rotating by the desired angle theta. These are some numerical simulations. I don't know how much time I have, but one nice property of surface code is that the logical error rate basically exponentially decreases with respect to the physical error rate if your physical error rate is below a certain threshold, and that's what we do. That's what we realize for Clifford gates, and this would be true for T-gate as well, but we're not using T-gate here. But for the ancilla state preparation, our logical error rate approaches to p over 15. Okay, there are some higher order term, order p square, but when you actually assume that your sort of physical error rate is 0.01%, then this is very negligible. Okay, and under this assumption, our architecture, if you have 10,000 physical qubits with error rate 0.01%, our architecture can perform 117 million sort of Clifford operations, physical Clifford operations, and over 37,000 phase rotation operations. And there are certain advantages of using our architecture. And one of them is when what happens sort of the calculation speed. So assuming that we have the 64 logical qubit device, and assuming that in our architecture you can use, it takes 1 unit time to implement 1 gate. In the conventional FTQC architecture, in the literature, you'll find that as you increase the number of logical qubits, this speed decreases. But in our case, and this is solely because of implementing T-gates. Okay, so but in our case, we are not implementing logical T-gate directly, so our calculation speed is quite good. The other thing is that by 47 qubits, we have Fugaku, our supercomputer, and it can simulate up until 47 qubits. The second thing is on quantum volume. Cross et al. Defined this quantum volume, and in that paper, they actually estimated that NIST device's quantum volume is 2 to the power 37. But in our case, by virtue of using 64 logical qubits, our quantum volume increases to 2 over 64. Okay, and this is a summary. We are sort of trying to replace T-gate by arbitrary phase rotation gate, which is not error corrected, but we have done some numerical estimation, and our architecture can surpass existing architectures on 10,000 physical qubits, and will create 64 logical qubits. And yeah, some applications. Thank you very much.